When mathematician James Simons built the Medallion Fund, he operated on a strict premise. Human domain expertise, driven by intuition and natural language, is inherently noisy. To extract consistent profit from the chaos of financial markets, he relied on the pure deterministic signal of mathematical structure. Modern artificial intelligence system architecture suffers from this exact noise problem. When a user submits a prompt, they use human language, which is vague, heavily contextual, and loaded with unspoken assumptions. Routing this unstructured text directly into a software execution environment carries immense operational consequences. System latency spikes as the machine pauses to interpret meaning, inference costs soar, and semantic drift occurs as the AI slowly loses track of the original objective over a long session. Large language models operate on probability, constantly guessing the most likely intent behind a user's words. But a software environment like a game engine loop requires absolute determinism. It evaluates state and updates logic at 60 frames per second, where a probabilistic guess means a system crash. Achieving agentic reliability requires a semantic compiler, a system cascade capable of filtering the chaos of human intent into the pure, zero-latency signal required for bare metal execution. That execution layer is GEM-VP, a minimalist runtime environment. To achieve absolute determinism, this engine bypasses traditional JavaScript and its garbage collection mechanism entirely. Garbage collection is an automated memory management process that periodically pauses system execution to clean up unused data, causing unpredictable latency spikes. This diagram maps a 64 kilobyte block of WebAssembly linear memory, a low-level format executing at near-native speeds. By sectioning this into strict blocks, the engine defines precise addresses for the header, input state, entity table, and scratchpad. A JavaScript sensor detects user interaction, pushing a numeric coordinate directly into the 0x0400 memory slot. There is no complex object creation, just raw numbers writing to static addresses. To manipulate this memory map, the engine utilizes ExplicitPrompt, a programming language designed as a strict subset of NLP3. NLP3, or Natural Language Programming, is a framework that integrates human communication patterns with computational language processing. ExplicitPrompt operates on a Forth-inspired postfix syntax. Postfix syntax, also known as reverse Polish notation, is a mathematical notation in which every operator follows all of its operands. A user pushes the number 5, pushes the number 3, and then applies the addition command to resolve the stack. Forcing human inputs into postfix commands that write directly to a static memory map guarantees execution speed, eliminating the instability of object-oriented game states. The core of this logic is the kernel, a lightweight execution model running in under 100 lines of code. It reads operations sequentially and evaluates them against a strictly scoped dictionary of predefined words. This diagram visualizes a vertical data stack demonstrating postfix mechanics. A text string, sunlit codegrass, is pushed downward into the stack. Then the command drops in to pop the string from the top and execute a bender flash. To ensure the language remains grounded, ExplicitPrompt requires visual, auditory, and kinesthetic anchors. The stack splits the command, routing elements to distinct logical nodes, binding the text explicitly to sensory data arrays. Before any logic executes, it must pass through a pace-lead control mechanism. The kernel assesses the user's current context and sensory state, the pace, before it permits the logic to guide the state toward a new outcome, the lead. This rigid, stack-based grammar forces human language into strict boundaries because the operands must exist before the operation can execute. The architecture prevents the runaway logic loops common in standard autonomous AI agents. Long-running AI logic faces a constant threat, Gresham's law of language. Just as bad money drives out good money in an economy, vague, generalized language slowly displaces strict technical definitions in a language model. If a user types the word bank, it could mean a financial institution, or it could mean the edge of a river. Standard language models will often guess based on training weights, risking a catastrophic overwrite of the system state with the wrong context. The architectural solution is the Explicifier. It acts as a semantic parser sitting between the user's prompt and the kernel, operating as a strict semantic mint that validates words before they execute. This diagram outlines a three-tier namespace stack. Layer 0 is the gold GAR, containing immutable kernel primitives. Layer 1 is the currency, holding vetted domain logic. Layer 2 is pocket change, containing ephemeral session data. When a collision occurs, like the word scale defined in Layer 1 as a musical tool, but the user is in a kitchen context, the Explicifier rejects the overwrite. Instead, it forks the definition, minting a new temporary command for the kitchen scale and pushing it safely into the Layer 2 session stack. Isolating definitions within a tiered namespace ensures the system maintains strict objective identity, where A is always A, throughout the entire runtime. This structure enables a symbiotic language between user and machine, reducing runtime inference costs by turning probabilistic intent into local code. When the Explicifier encounters an ambiguous prompt it cannot resolve locally, it executes a first-pass routing. It sends a request to an external LLM API. An LLM API is an interface that allows the local software to send data to a massive, cloud-hosted large language model for processing. The cloud model outputs a strictly formatted postfix word, pinned to its specific V.A.K anchors. This ensures the response is not just conversational text, but an executable instruction with rigid sensory data attached. This newly minted word is instantly downloaded and slotted into the system's local WebAssembly dictionary. As the session continues, the user will eventually input that exact command again. This triggers the second pass routing. The Explicifier scans the input, checks the local dictionary, and finds a perfect, mathematically precise match. Because the meaning is established and locked, the system completely bypasses the cloud LLM. The logic routes directly into the local WebAssembly kernel. This short circuit transforms probabilistic guessing into immediate deterministic execution. Per-action API costs drop to 0, and execution latency falls below 10 milliseconds. A fully populated dictionary functions as a locally hosted ontology, a comprehensive map of the system's logic requiring 0 compute cost to access. The user and the AI converge on a highly precise shorthand. The friction of natural language is removed, leaving a shared vocabulary that executes instantly. Simons demonstrated that mastering complex systems requires isolating the pure signal and ruthlessly discarding the noise. The explicit prompt architecture applies this exact filtration to human language. The engine strips away conversational ambiguity, leaving only executable intent. By grounding every word in sensory anchors and stack logic, we restore identity to the machine's reasoning. Agentic reliability is built by forcing intent into the lowest, most deterministic level of the machine. Simply expanding a context window forces a model to guess. Compilation forces it to execute.